Hello, my name is Amber Ward. I currently major in physics at Cameron University. I was fortunate enough to be selected to participate in the data-intensive scientific computing research experience for undergraduate students here at Notre Dame. For the past 10 weeks, I have worked under the guidance of Dr. Peter Garnovich and several of his graduate students, helping to construct a model to fit the light curve of a Type 2P supernova. Supernova are the result of an explosion of a supergiant star, which means a star that has a mass of at least 8 times that of our Sun. When these massive stars explode, it is due to an unstable core which collapses. Hence, these are also known as core collapse supernovae. There are 2 major classification schemas for sorting supernovae, Type 1 and Type 2. Type 1a is what is often used for measuring cosmological distances, and they have been used to show that the universe is not only expanding, but that expansion is accelerating. There are some important differences between Type 1a and Type 2p supernovae, but they are similar enough to easily be mistaken for one another in observations, which results in error due to contamination. This is why it is important to formulate a method to accurately and efficiently differentiate between these 2 types of supernovae. So for the past 10 weeks, I have been working on constructing a model to fit the diverse and complicated light curve of a Type 2p supernovae using a combination of several specialized functions combined to generalize an overall model for sorting the Type 2p from Type 1a supernovae. This graph shows the peak of the luminosity of a Type 2p supernovae after explosion, which was captured by the Kepler telescope. The initial rise is best fit using a physically motivated model of Robinach and Waxman. I used a chi-square and least square function to fit the curve with a reduced chi-square value of 1.8. An ideal fit would produce a reduced chi-square value as close to 1 as possible. So while my model has room for improvement, you can see that the fit is well represented, even with a value that isn't optimal. The next more complicated portion was fitting the decay of the light curve. This required a combination of 3 different functions. The first part of the light curve is handled by a half-Gaussian function, which covers the decline down to the plateau phase. The plateau phase is then handled by a Fermi-Dirac function, which also transitions the rapid decline after the plateau into the decay portion. The decay portion is then handled by a simple linear function. The combination of these 3 functions, in conjunction with the initial rise function, produce a good working model to help distinguish Type 2p supernova from a Type 1a, which will help alleviate the costly and time-consuming methods of having to take and analyze individual spectra. Also providing a timely solution for reducing sample contamination in future research. This will be an ongoing effort in the scientific community, and I'm very grateful for the opportunity to be a part of such an amazing group of people. Thank you.